And today we have a great pleasure of hearing a talk and seeing a talk by Professor Alfonson Bandeira, who will talk about computational hardness of hypothesis testing and quiet plantings. Alfonso, the audience is all yours. I just ask everyone to mute during your talk and unmute for asking questions as you see appropriate. Alfonso, go ahead.
Thank you. Thanks so much for the invitation, introduction. It's a pleasure to talk here. I hope, let me make sure first that I'll share the right thing. Can you see my slides and none of the Zoom stuff? Yeah, okay.
Yep.
Yeah, I hope that I get to see you all in an original FFT in a upcoming February soon. Okay, so I'm going to talk about computational hardness of hypothesis testing and in general statistical inference in a way, and the quiet plantings, which in a sense is a lot less statistical, but one can use these ideas behind understanding the hardness of computational of statistical inference to say something about actually optimization. Okay, so we'll get to this. So before I get to it, I want to say that if anyone has any questions, please interrupt. I'm very happy to clarify anything. And if I don't get to the end, it's perfectly fine. Particularly if I don't talk about quiet plantings, it's perfectly okay. The rest is self-contained. So please don't hesitate in interrupting if anything is not clear at all. I'll start with just a very brief, big overview, and then I'll get into something a bit more specific. But please do ask questions. So what I'm interested in general is understanding what are the limits of what one can learn from a data set, right? So here I'm being extremely vague at the moment, but if there's something you want to learn, something you want to estimate, and you have a certain amount of data, what are the limits? How can we describe what are the limits from the very mathematical viewpoint, right? Which methods work and why, right? And I'll let you enjoy this very clever cartoon. And what are the bottlenecks to learning? So are they, or to doing inference? Are the bottlenecks about quality of data, quantity of data? Are the bottlenecks about algorithms, about intrinsic computational hardness, or we just don't know how to develop the right algorithms, or are they about computational power? Where do the bottlenecks lie when we try to learn or to do inference? And when is it that we can a posteriori evaluate or certify what we've learned or the problems that we've solved? And we'll get to this a bit in the end. We'll have to do with this quiet planting business that I mentioned, but haven't really described yet. Yeah, so in this very, very general question of limits of what one can learn, that has of course been asked for a long, long time, right? In particular from the very statistical and information theoretical side of things. Particularly the statistical one, this dates back at least to the 1700s, right? The whole notion of Bayesian statistics already has in it an inherent uncertainty that when I have a posterior distribution for some parameter that I want to estimate, it's already very inherent there, the amount of uncertainty by how much, say, variance the posterior distribution has. Right, in the last 100 years, this kind of idea has really gotten a lot more mature. Right, there's introductions of things like Fisher information that somehow measures the amount of information in a sample, albeit in a very local way. On the side of hypothesis testing, right, the Newman-Pearson lemma sort of completely answers the question from a statistical point of view for hypothesis testing when when it's simple hypothesis testing. What this means is a much simpler version of learning from data in which you just know that you're in either two states of the world, state number one or state number two, and all you want to know is if the data is compatible with state number one or with state number two. You just want to know which one you're in. And then, of course, this more recently has become even much more mature. And in particular, I want to bring up the introduction of an appearance of information theory, right, which allows you to sort of measure the amount of information in a much less local way. And many of these ideas show up in what I'm about to talk. But I guess the point I want to make before I go on is that all this line of work tries to answer the question of when is it that there is enough information in the data? It says nothing about how to retrieve such information. It's just about the lower bounds that are presented and the limits that are established of this under this kind of framework are just of the style, you just don't have enough information in the data. The data is just as compatible with the truth as it is with some other alternative truth that is not true, but that might look just like it, and so you would never be able to learn. But of course, there's more to it than this, because when you have to learn and when you have to estimate, right, let it be in signal processing and machine learning and statistics, almost always you have to find the parameter, the signal, or the model that best fits the data. Right? So this is present, of course, in things like maximum likelihood estimation. When you're doing statistical estimations, one of the classical approaches, you have to maximize the likelihood. Even when you're doing more modern things like training neural networks, you're solving some form of optimization problem. Right? But optimization problems, they're computational problems, and they have their own challenges. Right? And one might ask, are the resulting computational tasks that arise when trying to learn or trying to infer, are they computationally feasible or not? And so we know by now, or we believe very strongly by now, that many optimizational computational problems are actually difficult, right? What we call NP-hard, right? And the history of this is a lot more recent, right? I mean, I at least from my homework, it dates back to, or the question itself dates back to the 50s, right? There's this sort of amazing letter that Gödel wrote to von Neumann, where he asks, essentially, he asks von Neumann if there are problems that are a lot harder to solve than to sort of state the problem, right? And even to check the solution in a way which has to do with this NP hardness, but I don't really want to get into it. But Gödel I mean, my understanding was it was interested in understanding whether being a mathematician was computationally hard in a way. Right? It was interested in understanding whether algorithms could replace mathematicians, whether like theorem proving could be made automatic in a very efficient way. Because checking a proof for a theorem is usually, not always, but usually easier than finding it. And Gödel was interested in understanding whether there were problems that really had this computational characteristic, right? And he asked this to von Neumann, and there's this I highly recommend looking up this and reading it. And John Nash also asked a similar question. He was interested more in the side of cryptography, but this kind of idea that there are problems that are inherently difficult is also present in the letter he wrote. And then it's got a lot more mature in the 70s with the whole theory of NP-hardness, which essentially says that there's many problems that they're all just as difficult. So if one is difficult, the others are also difficult. And since we've been for a long time trying to solve all of them essentially, and we haven't succeeded at solving any of them, then this means that they're probably all difficult. And proving this is hard is one of the millennium problems, as I'm sure all of you know, but we even without proving it, we sort of believe that all these problems are difficult. So the point is that there are computational tasks that are difficult. And so this motivates a very natural question is, should we be designing statistical models and inference models and learning models and so on, so that we don't fall in a trap of getting into one of these NP-hard problems? Should we do it so that optimization is easy? This is one of the reasons why, in a lot of the learning statistics and so on, there's a lot of linearity and convexity. It's not the only reason, but can certainly be viewed as one of the reasons. But as I'm sure many of you know, these days we don't necessarily have things that are linear and convex and so on. I mean, training of neural networks is a good example, but I'll give you some examples that are a bit easier to grasp in a short talk. So let me give you an example that's sort of very close to heart. Okay, so I'm using graphs and networks to give my examples just because they're a bit more visual and easier to think about. But actually, the example I'm going to dive in later is with matrices. But let's say that I have, I'm trying to learn community structure in house. I know exactly how the data was generated. So I'm in a setting where everything is well defined, right? So that I can do some mathematics around it. And so here I have a random graph that has some planted community structure. I draw it at random, and as n nodes, and has n over 2 nodes on the left, n over 2 nodes on the right, right? I pick, say, at random, half of them I color blue, half of them I color red. And now the edges of this graph going away. Every pair of nodes, independently, I either put an edge with probability P if they have the same color, or if they have a different color, I put an edge with probability Q. And so this means that if P is a lot bigger than Q, then this graph is much more connected within the caller than across the caller, sort of a community structure. And now I can the question of P is bigger than Q just by looking at the graph. Can I estimate the callers? Right. Another way to put this is I draw this random graph. I now jumble everything together, take away the call, and ask, can we recover calls? Right. I mean, statistical inference questions usually don't come of this type, but this is certainly a question of exactly that style, where I know exactly how the data was generated. There's some hidden parameters, and I want to estimate them. Right? And here, the hidden parameters is the partition. Right? They're the latent or hidden variables. So now you sit down, you try to work this out and say, clearly, if P is much bigger than Q, this is very easy. If P is the same as Q, this is impossible. Right? And there's somewhere in the middle, there's a sweet spot. Right? So sit down, try to work this out, and you see that to see the sweet spot, the right kind of scaling for P and Q is where the average degree is logarithmic. So you set P to be alpha log n over n, Q to be beta log n over n. Right. For those of you that are familiar with random graph theory, this is around the connectivity threshold, because if the graph isn't connected, then we won't be able to know the communities for every node. And then one can prove that if this simple equation, right, square root alpha minus square root beta bigger than square root 2 is satisfied, then the minimum bisection coincides with the true communities. Minimum bisection is simply grabbing the graph, splitting it into two equally sized parts, such that you cut the least amount of edges in between. This would be the most natural algorithm in this case. Corresponds to maximum likelihood estimator, to the maximum a posteriori estimator, if you take the Bayesian approach, and so on and so forth. So far, so good. And you can also show that this is essentially an if and only if. If it's smaller than root 2, then you can prove that nothing works using the techniques, say, of information theory and so on. Okay. Now, the problem is that minimum bisection is an NP-hard problem. Okay. So given a graph, computing the minimum bisection is a hard problem. What does this mean? Is that we believe the algorithm that is efficient and can compute the minimum bisection for every graph. That doesn't mean that if I give you a specific graph, that it's not easy for that graph, right? If I give you a graph that has just two disconnected subgraphs of the same size, then of course computing a bisection is very easy. You just see that it's two separate components, right? But in general, it's an NP-hard problem. Okay, and now it's the interesting theorem. Exactly when the minimum bisection is giving you the true communities, one can show that actually minimum bisection can be computed efficiently. Okay, so exactly when it matters. I mean, I'm exaggerating a little because it might still matter to compute minimum bisection in other cases, but when it's statistically giving you the right answer, then it actually turns out to be computationally efficient to solve. Okay, this feels like a bit of a miracle. And the question I'm interested in answering or in investigating is, does this always happen? Is there a good reason for this to happen, or were we lucky? Okay, if there's any questions, I'm happy to stop and answer any questions, but here is one place where it seems that even though it was hard in this case, just so happens that with high probability, the graphs that get generated by this process, computing them in bisection is actually easy. Unfortunately, this doesn't seem to be always the case for all the problems. So now I'm going to give you the classical instance of where we believe this isn't the case. And there is some inherent computational difficulty. And this is the hidden click problem. Okay? So I'm going to again draw a random graph model. This is a graph on n nodes, very similar to the one before, but without community structure, where every pair of nodes gets connected with probability, in this case, a half. So it's like uniform over all possible graphs of size. Of n nodes. And now here's another, what we call a planted sort of counterpart to this model, where we draw the same graph, but then we pick k nodes at random, let's say 4 nodes here at random, and then we add a click, right? What I mean by this is we just connect every single edge between those nodes. Okay? If there was an edge already there, we don't put a second edge. We just don't put anything if there's already there, but now there's a click on these k nodes. Okay, and now here's a hypothesis testing question. I give you a graph. You promise that it either comes from this distribution or what we call, let's say the Q distribution, or I give you one that comes from the planted distribution, okay, or the Q or the null. Okay? So I give you a graph. I promise to you that it either comes from the left or it comes from the right. You just have to tell me which side did it come from. right? What was it a graph where I planted a click or not? So of course, the natural algorithm, if you don't think in terms of being computationally efficient, is simply to compute the largest click, see if there is a large click on the right. Okay, so you have to see now, in order to see when this works, you have to see what is the largest click when you don't touch the graph, when you don't tamper with it. And it's not so hard to show that the largest click is smaller or equal than 2 log n on the left, right? It's basically a union bound. Okay, proving that it's actually 2 log n takes a little more work, but proving that it's smaller or equal than 2 log n is easy. Clearly on the right, I just added a click of size k. So clearly the click size is bigger or equal than k. So this means that when k is bigger than 2 log n, these two graphs look statistically very, very different, right? And all this is, with high probability, and it concentrates very, very quickly. And so essentially, if n is large and you draw from these distributions, you're always going to see bigger or equal than k, and you're always going to see smaller or equal than 2 log n. And so when k is bigger than 2 log n, these are very, very, the statistical test of size of the largest click is a great statistical test. Unfortunately, it's computationally hard. Okay, now let's look at algorithms. So there's an algorithm from now over 20 years ago, okay, where it shows an efficient algorithm to distinguish these two objects, to do hypothesis testing efficiently with k bigger or equal than root n. Much, much bigger than 2 log n. And essentially, there's been no improvement since. And we believe that this is essentially non-improvable. Okay? To the point where this is used as a reduction primitive, meaning that if you have a problem, one argument people give is that, oh, your problem must be difficult because if you could solve your problem efficiently, then you could improve overall on Krivulevich-Sudakov. And we really believe this not to be possible, right? So traditional complexity theory works very much with these kinds of reductions. In this sort of statistical question is a lot harder because you have to reduce both the problem and the distribution of the input. But in this case, it is possible to reduce some problems to this. And this is how much sort of we believe that this is difficult. Okay? And this suggests a certain hypothesis, or what we call the statistical-computational gap hypothesis, that learning and statistical inference problems, and in particular, I'm going to talk today a lot about hypothesis testing, have sort of 3 phases to them, right? Sometimes there's just, like I'm formulating now in terms of signal-to-noise ratio, right? So signal-to-noise ratio could be quality of data or 1 over the noise or amount of the structure that was planted, like could be K, say. In the stochastic block model, it would be the strength of the communities, right? I use signal-to-noise ratio because I came to this from sort of image processing and signal processing, where the problems, in the problems there, the parameter really was a signal-to-noise ratio, but I'm using this in a very general term. It just means the strength of the signal when it's drowned in the data. And when the signal-noise ratio is too small, right? When the community structure is too small, when you have too little data, when the click is too small, then the problem is impossible, right? In the traditional sense of statistics and of information theory. There's just not enough information. Okay, then you can look at algorithms, and algorithms will start working from certain, right? Maybe an algorithm works from here on and so on. They sometimes need more signal-to-noise ratio than you can prove information theoretical lower bounds. And I hypothesize that sometimes there's fundamental gaps in the sense that the statistical threshold lies somewhere, and there is another threshold, a computational threshold, that is different, such that if you're in the left of this, the problem is impossible. If you're all the way in the right, the problem is easy in the sense that you can do it efficiently. But somewhere in the middle, there's what we call a hard phase, in which information theoretically speaking or statistically speaking, there is enough information in the data, but we really believe that there is intrinsic computational difficulty in the problem and that this cannot be retrieved efficiently. And so what I'm interested in is understanding what's going on, what makes a problem difficult, and how do I get understanding of where this computational threshold is, right? Because the computational threshold is really the one that matters in the sense, because as data goes bigger and bigger, we're never going to be able to get into places where only exponential time algorithms work or non-polynomial time algorithms work. And so the main question is, what makes a problem difficult? Right? And this is a sort of a somewhat vague, I mean, maybe not vague, but hard question to answer in general, of course. But this is sort of the central question: is what makes one of these inference or learning problems hard? Okay, so there's a few techniques in how to argue that a problem is difficult. Right? We're very far from being able to actually prove a problem is difficult. We have trouble doing this even in worst case analysis, but there are ways of arguing. So let me give you a few examples, and then what I'm going to do is I'm going to go into more specific about one technique and one problem. And so one is to use tools coming from statistical physics. So let me try to explain the idea in maybe 3 minutes or so. So take the stochastic block model example. Right? What you want to understand is something about the posterior of the node callers given the graph. Right? So this is a probability distribution on all the node callers. Let's say you think of the node callers as like, say, blue and the blue and red as plus and minus ones. Then really this is just a probability distribution over the hypercube. Perhaps a very complicated probability distribution over the hypercube, but the probability distribution over the hypercube nonetheless. And so statistical physicists have been studying these objects for a long time, right? You can imagine that you have maybe a bunch of particles, they have spins plus or minus ones. You take a random model of how the particles, how they have their spin configuration. Okay? And just like in spins, like in spin glasses and so on, you would expect that particles nearby sort of interact with each other, or that the joint distribution is given by many pairwise interactions, for example. If you think about it, this also sort of happens in the posterior of the stochastic block model, right? Because the interaction between the posterior has to do with whether pairs of nodes have an edge joining them or not, and this is also a pairwise thing. And now people in statistical physics have been developing for many decades now tools to understand when is it that these distributions are simple or complicated. When is it that they have phase transitions, right? To understand phase transition materials. And it turns out that one can borrow these techniques to predict phase transitions in the problems, in these inference problems, and they correspond to computational thresholds. Okay, so I won't say much more. I can chat about it later during questions if there's any more, but this is one technique that sort of gives amazingly accurate results, but sort of very somewhat non-rigorous for sure. Or there's lots and lots. There's many more conjectures than theorems, but the conjectures imply very precise predictions that seem to all be matched in practice when we try algorithms. Another option is to restrict ourselves. So what we'd like to do is restrict ourselves to efficient algorithms. Now, the set of efficient algorithms is sort of difficult to mathematically study. So instead, one can try to restrict ourselves to say, we can only use low degree polynomials of the data, right? And so we can ask, what is it that we can answer if we're only allowed to take low degree polynomials of data, right? And now we can do math a lot more easily. So this turns out to be a very fruitful thing to consider as well. And there's many other versions of restricted classes of algorithms that one could consider, right? Sort of analogs of surrogates of the set of efficient algorithms, right? And there's a few more that I won't discuss, but I'm happy to discuss a bit later. So what I'm going to talk about in this talk is a version of this what if we can only use low degree polynomials of the data for a specific problem in spiked matrix model and sparse PCA. Okay. So I guess if there's any questions, I'm happy to. This is a good place for questions because now I'm going to get a bit more specific. Right, so far was quite high level. I'm going to get more specific in a model, and so I'll wait the 10 seconds in case there's any question. So this part is joint work with a wonderful set of students and.
Alfonso, sorry for interruption.
Yeah, of course.
A question. So the second type of approach that you said, that would in some sense rule out spectral methods. Would
yes.
That be true?
So,
that is to say, you don't want to compute eigenvectors of the graph Laplacian or adjacency metrics, right?
Yeah. In fact, spectral methods are going to make an appearance quite a bit. So spectral methods are a version of a low degree polynomial, because I haven't said how low, what I mean by low, but low is like degree log n. And this is exactly to capture a power method type algorithm, which will compute eigenvalues and eigenvectors. So by low, I don't mean like degree 3. I mean actually comparable to spectral methods. That's really what I have in mind. We'll maybe be a bit more clear later, but this is a great point. This is really hitting on this is really hitting at the crux of the matter. Yes.
All right. Thanks.
But yeah, I realized maybe it should be called something else, because I realize low degree sometimes might seem like it's 2 or 3, but okay, maybe this will be more clear in a second. So what is this low degree method, right? So this comes motivated from the so-called sum of squares hierarchy, right? Which is a certain hierarchy of algorithms that itself comes motivated from certain things in algebraic geometry and so on. I'll sort of skip all this motivation and just present the low degree method as a separate thing, right? This, in the way that it's stated, was introduced in Hopkins and Storr, motivated by this other, right? This body of literature in sum of squares, in the sum of squares hierarchy, and trying to build pseudo solutions for it. But for our sake, we don't need to get into sum of squares. So the goal here is to do hypothesis testing. There's variants of the low degree method for actual estimation and so on, but this is much more transparent in hypothesis testing, and that's what I'm going to focus on. And so the goal is to do hypothesis testing between two distributions with error going to 0, right? With error being, I'm using here the computer science notation, little o of 1 just means going to 0 as n goes to infinity. My n is always going to infinity. You could say, yeah, maybe we're interested just in doing hypothesis testing with, say, better than random chance with accuracy 70% or something. Turns out here, the right question is really to ask for the error to go to 0, because that's when hypothesis testing is related to estimation. Okay? And I'm happy to answer questions about this, but sort of this is the right level of error to ask for. And the hypothesis testing will be between two distributions, what we call the null model. Think of it as just a graph without any clique, right? Where your sample, you get only one sample, but a big sample, right? N is going to infinity, sort of the dimension of the sample, if you will. Then either you get something from the null model that has absolutely no signal whatsoever, or something from a planted model where there is some signal, right? So think of it as the graph without any clique and the graph with a clique. You get one sample, but you study it as the graph gets bigger and bigger. Okay. And you ask, when is it that you can do hypothesis testing between these two distributions? Okay. So of course, you know, if you don't care about computation, even Pearson answered this question already for us. We know exactly when it's possible and so on. But we're interested in understanding when is it computationally feasible. And so here's the idea, is to ask, is there a low degree polynomial of the data, right? A polynomial f of y that is big when y comes from the distribution and close to 0 when y comes from the null model, right? In the clique, I would want something like f of y is, if there's a big clique, give me something very large. If there's no clique, give me 0, right? But of course, this unfortunately is not a low degree polynomial. But now you ask, is there a low degree polynomial that behaves in a way like this? This still seems like difficult to answer. However, the key idea is that you can now massage this into something that becomes easy to answer. And you can ask, can I find a low degree polynomial that is big under P and small under Q in this particular sense, that it maximizes the mean under P divided by the fluctuations in the Q. Now, the point is that you wrote things in a very L2 way, and so we can actually answer this question. But the idea will be to compute this object, right? The maximum over polynomials of degree at most t, and maximizing the mean under P divided by the fluctuations in the Q. Okay? So now let's very quickly do some linear algebra. Right, so I want to make this, I want to transform this into sort of an L2 problem. So I want all the integrals to be under Q. So first I do a change of variables, right? So now everything is under Q, and the thing that is the change of variables is just that what we call the likelihood ratio, or statisticians call the likelihood ratio, right? Which is exactly the test that Neiman Pearson would tell you to use, for those of you that are familiar with that side of statistics. Okay, but so okay, I didn't do anything, just a change of variables, right? By this I mean the density of P and the density of Q. Okay. Now what I have is just an inner product, right? This is just an inner product under Q, right? And this is a norm under Q, right? L2 of Q. Okay. So really what I have is that I take the maximum of f of degree d, or at most t, of the inner product of the likelihood ratio with f divided by the norm of f, but this is just a projection, right? The answer to this is just, you take the likelihood ratio, you take this function L, and you project it on the subspace of degree D polynomials. Okay? And the value of this, then, if you project, is just the norm of this projection. Okay, that's all. The point is that we massage the problem in a way that's now a very like L2 linear algebra problem, and now we can answer it. I mean, we still need to compute this, but at least it looks like now something that we can potentially answer. Okay, for the statisticians in the room, notice the connection with Lecombe contiguity. For the non-statisticians, just ignore this comment. I'm happy to talk more about it later. So we know that this is the value for this maximizing. Now, intuitively speaking, if I can make this grow really, really large and go to infinity, it means that the mean under P is much, much bigger than fluctuation. So it should be a very good test. If this is very small, shouldn't be that good of a test. So heuristically, if this number or this quantity goes to infinity with n, then the polynomials can distinguish between these two distributions. If it stays bounded, they cannot. Okay? Because if they stay bounded, it means the fluctuations in their Q are of the same order as the mean under P, and so you would not be able to distinguish them with probability going to 0. Okay, here's the conjecture. I mean, writing an actual conjecture is actually quite difficult, so I'm doing here an informal variant, where by informal I mean I haven't told you what nice is. But for nice distributions, essentially any that you might think of in this context will be nice. For nice distributions, if the likelihood ratio is bounded for some degree that's bigger than log n, and again, this is what I mean by the degree is log n. And you might think, why would we take degree log n? Computing a polynomial of degree log n might take time n to the log n, which is not polynomial. The point is that we need to be able to capture spectral algorithms. And taking the leading eigenvalue of a matrix is a bit like a polynomial of degree log n, because to do the power method, you should hit it roughly log n times. And so this is why you sort of need this log n. This is the right scale to look at things. And then if this is bounded for d bigger than log n, then there is no polynomial time algorithm that can distinguish between P and Q with success probability going to 1. Right? So with probability of error going to 0. And sort of the heuristic to have in mind is that degree d polynomials correspond roughly to algorithms of time n to the d. Again, with this catch that this theta to the tilde just means I might be ignoring log n factors or polylogarithmic factors in this exponent, right? Exactly because of this spectral algorithm business. But this is sort of the picture that one should have in mind. And nice, maybe I can tell you what is not nice distributions. If you hide algebra inside some of these problems, let me just say this. If you hide some finite field algebra inside these problems, these methods won't be able to tell them. Won't be able to see, like if you hide it well, and so this would be distributions that are not nice. But if you have things like Gaussians or any kind of sort of enough randomness, this won't be a problem. And so one can argue some theorems in the direction of this actually is some theorems suggesting that this conjecture is true. There's a few suggestions. One is that, in the examples that we try, it gives the exact right answer. And others, you can actually prove something. So one can prove that, indeed, this implies that no spectral algorithm can work. By a spectral algorithm, I mean, essentially, you build a matrix whose entries are polynomials of the data, low-degree polynomials, and then you take the spectrum of it. So these algorithms won't work. Or you take the leading eigenvalue or eigenvector. And there's reasons to believe that the spectral methods are as powerful as the sum of squares hierarchy, which there's reason to believe that this hierarchy is sort of optimal for a lot of these average case problems. So, I mean, I know that there's a lot of like reasons to believe in my description, but these are sort of theoretical reasons to believe, not just experiments. But let me not get into why they're just reasons and not actual theorems, for now at least. Okay. So here's that. I need to convince you, though, I think, that I can actually compute this for any interesting problem. Otherwise, this is all a moot point. So here's a model I really like to study these problems on, and this is the Gaussian additive model. Okay? So this is a particular null versus planted model, in which in the planted model, there is a signal distribution over a signal, which is this P. Right, so this is the distribution of the thing I'm planting. So you should think of P as a set of signals. you draw at random from them. And then if you're in the planted model, you add Gaussian noise. If you're in the null model, you skip adding the signal and you have just Gaussian noise. And now all you have to do is to distinguish, is there even noise there or not? And the thing you should have in mind is that doing hypothesis testing between this is sort of should be easier than estimating X from Y, which would sound like a more typical signal processing problem, right? So, and what we're interested in here is giving lower bounds, right? Proving things that proving that or arguing that something can be done. And so we're going to easier hypothesis testing problem. Right? And this is really why the error needs to go to 0, because in order to say something about estimation, it really corresponds to the hypothesis problem error of hypothesis testing goes to 0. Okay. So here's the proof of how to compute the norm of the likelihood ratio. Okay. Put it here since it's being recorded. You can pause the recording and see it, but I won't go to the proof. It just said actually computing the likelihood ratio is not so easy, but computing its L2 norm is actually pretty easy, right? And it uses some Hermite polynomial. Point. The norm of this truncated likelihood or the projected likelihood ratio is given by formula for it. Effectively, distribution of this distribution, two independent the inner product between these two replicates. And you take the moment generating function of this, but you truncate it in D, and this truncation means the real definition is here. Right? Why truncating in the likelihood ratio corresponds to truncating the polynomials it's not clear at all that this is satisfied, because right, this is a function of the overlap, while this is a function of the. It turns out to be this very nice formula, and the point is completely described with respect to moments of overlap. So it's completely described with respect to moments of the inner product of two independent draws from P, and so this is something that one could, at least for many P. Okay? So let me now give you an example, right? I mean, I gave you I sort of, this was a meta example of discussion edited model. Let me now talk about a more specific example, right? An example I like are models. Okay? So here's the problem. I have a matrix that has a rank 1 component. A part with signal has a rank 1, what we call a spike. Okay, so the signal here, a vector 1. Okay, and the way we get it is we get the matrix Y is equal to lambda, which is the signal to noise ratio, right? How strong V is. VV transpose matrix, which means matrix that by n just full of independent Gaussian. So you just need them to be symmetric. Okay, so we know from and now the goal is, when is it that we can detect or recover V for this? When is it that we say W? And of course, this is in the model Gaussian, and form P, a vector, and write lambda VV transpose, and that can just be my distribution P. And now we know from random matrix theory, in particular from the work of Beitman-Arus and Pechet, that something happens. And if lambda is bigger than 1, an eigenvalue pops out in the single random component, and you start seeing it. And if now, if something pops out of the support, of course you can distinguish, because if there's something outside of the support, that tells you how to distinguish. If it doesn't pop out of the support, maybe you can still do some other things to distinguish, but actually 1 can be below 1, it can't be done. Now, if you like to think more in terms of principal component analysis and shared matrices and sample covariance matrices, there's a completely analogous, in fact, thought of for this model. Track of is a bit easier to explain, but what I'm going to say applies just as well for the wish model. So In particular, it means that in this story that I told, there's no computational issues, right? Either you see an eigenvalue outside of support, you can just compute the eigenvalues, or you don't, and this completely tells you when is it possible or not. But let's say that you know a bit more about the vector. Let's say in particular that you know the vector is sparse. Okay? So let's say that for rho, right, some rho smaller than 1, that the vector is rho n sparse. Okay, so it has many, many zero components, and because it has norm fixed to 1, the ones that are non-zero are of course larger, right? So potentially much easier to detect. Can you now detect it if the lambda is smaller than 1? So since lambda is smaller than 1, right? No eigenvalue will pop out outside of the support. And you really have to use the fact that the vector is sparse in order to be able to recover. And because I'm going to prove lower bounds, right? I'm going to argue that things can't be done. Then I'm going to even make my life harder by not just saying that it's sparse, but even tell you exactly what the distribution is. Right? It's drawn uniform from the vectors that are 0 and plus or minus 1, normalized to have norm 1, to have that sparsity. Okay? And I put lambda just shy of minus 1. Think of lambda as 0.99. You have just shy of being able to see it in the support, but you can't. But you have almost enough signal for you to be able to see it in the support. Okay, and now you can ask for which levels of sparsity can you do this? Right? The more sparsity, so the smaller the rho, the more signal there is, because the more the components that are non-zero become very large, and you might see them in the matrix. Okay, so let's see the history of this. So if you ignore computation, constant rho is already enough. Unfortunately, the algorithm consists of trying over all possible sparse vectors, and this is exponential if rho is constant. Now, if you ask for efficient algorithms, we see again the square root n behavior like in plain-to-clique. And so rho needs to go, the sparsity of rho needs to go all the way to root n for all the known efficient algorithms. And essentially, this is where we think the story is at. I mean, there is lots of evidence for computational gaps, some of which a reduction from right here, a reduction from plain-to-clique, but by now there's lots and lots of other evidence. I should mention maybe that, right, so the plain-to-clique problem, because the size of the largest clique on the unplanted graph is size log n, you can actually do it in time n log n, while here it should be a lot harder. Right, so sort of this evidence now tells you that that should be even much, much harder than plain-to-clique, but right, it's not polynomial time anyway. Okay, so let's see what this technique gives here. So I mean, you can just do the calculation, right? It's clearly in this Gaussian model, so we can just compute these things, right? And so figure out some way to, I mean, some tools to compute now these likelihood ratios for this Gaussian model. And basically what one shows is if you lambda is smaller than 1, think of just shy of 1, then if the degree is smaller than rho square n, then you're at a place where polynomials of that degree can do it. And if d is bigger than rho square n, then they can do it. And so what this suggests is that an algorithm, in order to be able to do sparse PCA, to be able to tell apart these, and in particular to estimate the vector, it turns out, should require, in order to exploit rho n sparsity, it should require, or this method predicts it requires exactly exponential rho square n computation. Okay, so a few things. So if rho is constant, it tells you the exponential in n, like we expected. When rho is 1 over square root n, it gives you polynomial, right? Because there's all sorts of log factors hidden here, but basically is when the thing gets out of the exponent. And an interesting thing is that this suggests sort of a strange computational complexity, because looking over all sparse vectors takes time exponential rho n, not exponential rho square n. So if you take like rho to be, say, 1 over the 4th root of n, these are very different. Okay, so that was a bit surprising, but turns out after you see this, that it's actually easy to come up with an algorithm that takes this time. Right, and in fact, around the time when we had this lower bound, there was also an algorithm independently discovered with this running time. So maybe not easy, but it's also possible to do even without the lower bound. But once we had this lower bound and we knew to look for this complexity, was actually quite easy to, because essentially the algorithm, or an algorithm, the other algorithm that shows up is a bit different, but an algorithm is to just look over all sparse vectors with this sparsity, which is sort of gets motivated by this lower bound. Okay, but the point I want to make here, so this is still sub-exponential. So I mean, it won't at least I don't feel like it'll be practical, or at least not, you know, we shouldn't be running sub-exponential algorithms. That being said, it does suggests sort of that this technique is giving something very, very accurate, right? Because the technique suggested a certain computational complexity, right? To the granularity where it even suggested the exponent in the sub-exponential complexity. It was sort of a non-trivial complexity, and it seems to actually be accurate, right? So sort of in part in the business of trying to sort of show that, I mean, to attack the conjecture, right? In sort of a scientific way of making falsifiable statements. This is a very like sort of precise statement that seems to not have been falsified. So it makes me more it makes me believe on this technique more, and it's sort of why I wanted to make such precise statements about the computational complexity. Okay, and none of the other techniques, at least, it's not clear how they can suggest this kind of granularity. Oh, René, do you have a question?
Yes, Alfonso.
Yeah, go ahead. Yeah.
I was curious as to how this might connect with results such as, the results from matrix completion or even low rank approximation of sparse plus low rank style decompositions, even with noise. So in that setting, you would get cases where you wouldn't have this sub-exponential computation. But those cases were not derived from a hypothesis testing perspective. So I was curious as to whether there is any connection with those previous results. I'm thinking, for instance, all of the line of work of Candes and Parillo, or maybe there is no connection.
Very interesting question. It's not obvious to me. That being said, one could definitely ask the question of, can this technique predict some type of computational hardness in those kinds of models? The problem is that, at least in the way I'm presenting it here, it really relies on this hypothesis testing framework. And I don't know what would, so, right, the planted model could be sparse plus low rank, but I don't know what the null model would be. So there is another problem where we have exactly this issue, which is tensor decomposition. So at a certain level of rank of a tensor, we believe tensor decomposition is difficult. But this, we believe, is actually very weak. We have very little evidence. And yeah, I've hit my head against the wall many times trying to figure out how to use this kinds of approaches there. But the problem is that I really don't know what a null model would look like. And now for this sparse and low rank, I haven't thought enough about to say that finding a null model is difficult. Maybe it's not, but I definitely will, motivated by your question. Yeah, so short answer, I don't know. I don't know how to use these techniques, but it's definitely a good place to try them.
I don't know if this would be the right answer, but in the sparse plus low rank, I guess you would need to say that W is the sparse part and use that to define the null model with some statistical model on the number of non-zero entries and things like that.
But so sometimes what happens is that, so you could try to do hypothesis testing between, I give you a matrix that's sparse plus low rank, or a matrix that's just, full rank, no sparse, it was not the sum of two special matrices, it was just a random garbage matrix. The problem is, and if you can't distinguish between the two, then it's convincing that you shouldn't be able to split the other one anyway. Now, the problem is that sometimes it might be difficult to split the matrix or to do tensor decomposition is the example I have in mind. But still, you can tell that it doesn't look just like a complete, say, Wigner matrix, because information might creep out in ways that you can't exploit to decompose, but you can exploit to know that you're in a strange matrix model. Does that make sense? This is the issue that we face quite a bit in some of these problems. But I will sit down and try this and see. Yeah, thanks for the question. It's a very good question. Yeah.
Thank you, Alfonso.
Yeah. Okay, so now actually, I'm now going to talk about quiet planting. So we're sort of done with statistics for now. And now I'm going to talk about optimization. Let's see how much time. How much time do I have? This is very short, this part, but
well,
I don't want to go over
until 3 o'clock for sure.
Oh, perfect. Okay. All right. So here, okay, now we're not talking about, I mean, it is related in a way, but let's put our minds in optimization. So here what we want to compute is the ground state of the so-called Sherrington-Kirkpatrick Hamiltonian. Right? This comes motivated from physics, but you don't need, the motivation is not important for this sake. W is a Wigner matrix, random Gaussian entries. And what we want to compute is the maximum over the hypercube, right? I do the 1/√n just to normalize things, of X transpose WX. If you're an optimizer, you're just taking a quadratic program where the coefficients are Gaussian, completely uniform, right? So this is now a random optimization problem. Not in the sense that you're optimizing a random function, but in the sense that you first draw your function at random and then you're trying to optimize that. And so now you can ask, what is the typical value of this problem? Like say, what is the expected value under the Wigner measure of this? Okay, so let's talk a little bit about this question. And this is the kind of questions that are very important in statistical physics. And this is why, you know, it's what Sherrington and Kirkpatrick were interested in. So this is a Wigner matrix. So this is the histogram of the eigenvalues of the Wigner matrix. Okay, right, these are the different eigenvalues, and this is how many eigenvalues are of roughly that size, right? So I turned this 90 degrees from before. And I'm only putting here the positive part. So now the largest eigenvalue of the Wigner matrix is 2. Okay? So I claim that Sk of W, but typically, right? So the largest eigenvalue of W is, of course, a random variable, but it concentrates very, very quickly around 2. Okay, and I claim that Sk then needs to be smaller or equal than that, right? This is a simple calculation to do because you take the max over X having norm 1, L2 norm 1, X transpose WX, right? Clearly, this is smaller or equal than that because, you know, I'm going from the hypercube to the sphere, and the sphere has the hypercube in it. And so this is then equal to the maximum eigenvalue of W. Okay? So clearly Sk needs to lie below this. Right? And in fact, we know the answer from the work of Parisi, from an unrigorous perspective, from like an unrigorous prediction, but still, you know, non-rigorous but extremely accurate. Down the number is defined from this prediction. It's not like a numeric prediction, and then was proven later mathematically. And so this is a complicated number. It's called the Parisi number, but it comes as a solution of some big-spline equation. But we know the number is around 1.5. Now it motivates the question of if I can try to design algorithms, efficient algorithms, to try to optimize this, in the hope that I can do, say, my algorithm in expectation with respect to the Wigner measure that's close to 1.5. Right? And there's been sort of a race to try to get better and better. Right? Random guess gets 0, greedy iteration gets something. If you take the eigenvector around and so on, and this is the amazing thing that there's an algorithm by Andrea Montanari from a few years ago that is able to get this minus epsilon for any epsilon in polynomial time, in runtime that depends on epsilon. Now, we don't really, I mean, the fact that the algorithm gives this is still conditioned on a certain conjecture in statistical physics, but one that is widely believed, right? And the algorithm is non-trivial. Now it's sort of, yeah, it's kind of amazing because this is a complicated optimization problem with a very complicated landscape. Right? For the statistical physicists in the room, it has what's so-called, or it's conjectured to have what's so-called full replica symmetry breaking. But there's another interesting thing, which is there's sort of a big gap here. And there's a big gap in a very precise sense, which is that if I now ask to give upper bounds on this quantity, so given a matrix W, I want you to compute, so this is the exercise. Given a matrix W, I want to compute f of W such that I know it's always bigger or equal than Sk of W for any W. I want f to be computationally efficient. And I want to measure the expected value of f under the Wigner model. Now, the point is that this needs to happen always, not just with high probability. Otherwise, I would just spit out 1.6 or something. Right? But then I measure how well it does in expectation. Right? So you can view this as giving lower bounds. I'm interested in giving upper bounds. I mean, there's a motivation from the viewpoint of certifying and so on, but there's also another motivation, which is the method that's viewed as being optimal for a lot of these questions is the sum of squares hierarchy. And because of its nature, it is a method of this style that approximates from this side. So from the theoretical viewpoint, is very interesting to understand if there is an inherent gap in the algorithm being of that style too. Okay. So now the point is that we believe that this gap is fundamental. That there is no function that can consistently give better than, there's no upper bound that consistently gives better than 2. Okay? And so I'm going to show you there's much evidence for this. I'm going to focus on this result. So here's how we prove something like this, or conditional uncertainty conjecture. We do something that I call a quiet planting. So we construct a random variable that looks like a Wigner matrix, but it's not. It's a tempered Wigner matrix, W prime, such that it satisfies two properties. One, the value of xk, the value of the quadratic program is close to 2, not 1.5. So it looks nothing like a Wigner matrix. And secondly, doing hypothesis testing between a real Wigner matrix and this tempered matrix that I built is computationally hard. I claim if I have such an object, if I can show the existence of such a distribution, then it means that I cannot give a certificate an upper bound better than 2. Why? Because if I had a certificate, an upper bound that was better than 2, you would provide a statistical test. Because if it consistently did better than 2, it would consistently do better than 2 under Wigner. However, under the tempered distribution, it could not, because under the tempered distribution, the value is really 2. So it would have to be bigger than 2. So I would have if there was an efficient way of upper bounding SK with something better than 2, I would get an efficient algorithm to do hypothesis testing. Now, the way we do this, I don't want to get into it, but sort of the spike model doesn't work. You need to do some spectral planting, right? You need to build this W prime somewhat carefully. But the point is that it doesn't matter how complicated the construction of W prime is, right? It doesn't need to be efficient or anything like this. The implication still follows, right? You just need to prove the existence of such a thing. So just before I finish, let me just mention that this can be, this kind of quiet planting and hardness of certification works also for other kind of problems. So here's one that I really like. So take a uniform d-regular graph on n nodes. So a graph with degree d on n nodes and uniform over all those. And now let's look at its chromatic number. So the number of colors, then the minimum number of colors such that you can color all the nodes in a way that no two neighbors have the same color. And now you can try to work out the combinatorics or random graph theory side of this, and you see that the typical chromatic number is d over 2 log d. So now you can ask the same thing I did for the SK model, you can do here. And here's the story. If you want to search for a coloring efficiently, there seems to be a gap of 2. And actually, the specific question of this gap of 2 goes back quite a few decades. And in the sense that it seems to be difficult if I give you around d over 2 log d colors for you to be able to color the graph efficiently so that no two neighbors have the same color. However, if I give you double the colors, this becomes easy. If I give you d plus 1 colors, this is extremely easy, right? Because every time you decide to put a color, they only have d neighbors. So even if they all happen to have all different colors, if you have d plus 1 colors, you still have 1 extra. So d plus 1 is sort of completely trivial. D over log d, not so much, but easy. Now, on the side of certifying from the left, turns out root d over 2 is what you can do with so-called a Hoffman bound. And when you try to prove hardness of certification and do plantings, the trivial stochastic block model planting stops at root d. And however, there is another model, which I can talk a bit about if someone has questions, which we call the equitable model, or even people in physics already call this the equitable model, that goes all the way to the Hoffman bound. And the point is that what this is doing is a form of spectral planting. So at least myself, I would not have been able, I would have not thought of using this kind of construction or constructing the quiet planting this way if it wasn't for the motivation of this spectral clustering, spectral planting here. And the interesting thing is that you can't just massage the spectrum of a graph and then hope that it's still a graph, right? And a matrix, you can massage the spectrum and it will still be a matrix. But if you have the adjacency matrix of a graph and you massage the spectrum, you might no longer have a graph, might not have ones and zeros. So you need to be very careful how one does this, but actually was this idea of massaging the graph that allows one to do this planting. And I could talk more about it if there's any question, but the point is completely answers this question, this technique. And yeah, I'm done. Sorry if I took any extra minute, I hope not. And yeah, happy to answer any questions and chat.
Thank you, Alfonso. Thank you very much for a great talk. Ladies and gentlemen, as always, please feel free to unmute yourself and ask questions to our speaker. So Alfonso, actually, if you wouldn't mind saying a few words about how you massage the graph adjacency matrix.
Yeah, so, okay. So basically, the structure you planned is an eigenvector of the adjacency matrix. And so it doesn't have this push out phenomenon. So there's something, okay, maybe I should say a few more words. So there's something very interesting. I mean, the first time I saw this theorem a few years ago, I found this sort of surprising, which is that you see that the spectral norm of W is 2, right? If you look at the eigenvalues, they stop at 2. And now you're adding a rank 1 component. And clearly, if you add something with lambda bigger than 2, you should definitely see something outside. That's kind of intuitive. I mean, even something like Jensen probably would imply that. What's really interesting about this is that it's enough for lambda to be bigger than 1. So when lambda is bigger than 1, somehow the vector you're planting, right, like gets pushed by all these eigenvectors up here. They somehow work together and make something pop out of the support that is sort of a linear combination of this that was planted on the top of this spectrum. And this is called sometimes the push out phenomena in the spike models. And so, however, if what you planted, if lambda VV transpose was an eigenvector of W, right, and in particular an eigenvector close to here, this would have not happened. Right? If you made sure that it was orthogonal to the top of the spectrum, this wouldn't have happened. And so really what we do is you do a construction. So this equitable block model is a model in which you make sure that the structure that you're planting, this signal, is not correlated with anything at the top of the spectrum of the random graph. It is, in fact, an eigenvector. So basically, I mean, it's kind of weird, but this construction is much, much more structured than this one. So this one is just the stochastic block model where essentially you do something like you take your D neighbors to be in other callers at random. You first fix the callers and then you take that to be at random. This one, you do much more. You ask not only that your D neighbors are in other callers, but that they're evenly distributed among other callers. And so by putting more signal in a way, you're actually making it more quiet because you're making it so that now it doesn't correlate with anything else because it becomes an eigenvector of the adjacency matrix. And then, of course, because it's an eigenvector of the adjacency matrix, you could find it that way. So then you need to just shake it a little, just shake it enough so that it's no longer an eigenvector, but you shake it after you plan. Is that, I mean, I'm probably speaking in, if this last sentence didn't make sense, that's okay, but the rest.
Thank you. That's clear. Thank you very much. Any other questions or comments? Well, if not, let me thank our speaker again. Thank you very much, Alfonso, for a great talk.
Pleasure.
Thank you, everyone. I hope to see you all next week for another installment of Faraway Fourier Talks.